In this video, I want to look at a few examples of the application of the method of undetermined coefficients for second-order non-homogeneous ODEs. The first one is given here. So what we want to do is find a particular solution for this ODE. Now, what we can see is that the right-hand side, r of x, actually includes numerous terms. We can simplify this complicated r of x by grouping like terms together and applying the principle of superposition for particular solutions. So let's group them as follows. So let's look at the polynomial and say that this is one r of x term. We'll look at the trigonometric functions and say that this is another term. And then finally, we have the exponential function here. So what we'll do is propose a particular solution of the form yp1 plus yp2 plus yp3. And this yp will be applicable for this ODE over here. And this is allowed by the principle of superposition. So recall from the previous video that what we're going to do is we have a table that gives us proposed solutions for different forms of non-homogeneous terms. So the first one, we have a polynomial of order n. Here an order is equal to 2. So we're going to propose that the particular solution, yp1, will be a polynomial of order 2 as well. And maybe I'm just going to stay consistent with my notes and just use a1 x squared plus a2 x plus a3. Okay, so this will constitute yp1. Now recall from the table in the previous video that if we have the summation of two sinusoidal functions, then we should propose something that is also the sum of two sinusoidal functions, one sine and one cosine. So this will constitute yp2. And then finally we have an exponential term, and so we will just say that we have ce to the 2x. And this will be yp3. So what we're going to do is substitute each particular solution into the ODE, and we're going to find the undetermined coefficients. So let's start with yp1. So for yp1, we will need its derivatives. So here we have yp1 prime is equal to 2a1x plus a2. And yp1 double prime, so the second derivative, we need the second derivative as given by the ODE here, is just 2a1. So what we're going to do here, we're going to substitute yp1, yp1 prime, and yp1 double prime into our ODE over here. And we're going to find our coefficients a1, a2, and a3. So we substitute into the ODE. And what do we have? So we have the second derivative, that's just 2a1, plus 2 times the first derivative, so 4a1x plus 2a2 minus 4 times the proposed particular solution itself. So that is minus 4a1 x squared minus 4a2x minus 4a3, and it is equal to our right-hand side. Now, remember that we're splitting up the non-homogeneous term into 3 non-homogeneous terms. So the first one is r1 of x, and the second one r2 of x, and r3 of x. So we will just be setting it equal to r1 of x. So that is 8x squared minus 3x plus 1. So what we need to do now is just equate like terms. So first, why don't we look at the x squares? So what we find here is that minus 4a1 should be equal to 8. Then we can look at the x terms. So what do we have? We have on the left-hand side 4a1, and then nothing until minus 4a2, and that is equal on the right-hand side to minus 3. So we've taken care of the x terms, so now all we have is the constant terms. So what do we have? We have 2a1 plus 2a2 minus 4a3 is equal to 1. 3 equations, 3 unknowns. Fairly easy to solve. We find that a1 will be equal to negative 2, a2 negative 5 over 4, and a3 15 over 8. Thus, this tells us that yp1 will be equal to minus 2 x squared minus 5 over 4 multiplied by x plus 15 over 8. So we found our first particular solution for a portion of this ODE. So we need to do the same thing for r2 of x and r3 of x. So recall we've proposed for yp2, we're saying that it is equal to b1 sine of x plus b2 cosine of x. So what we're going to do, we're going to take its derivatives, substitute into the ODE, and set equal to the right-hand side. The right-hand side for r2 of x, which is equal to 2 sine of x plus 4 cosine of x. So yp2 prime, the first derivative, is equal to b1 cosine of x minus b2 sine of x. The second derivative is equal to minus b1 sine of x minus b2 cosine of x. So what we're going to do is substitute in ODE and set equal to the right-hand side, which I'm just going to write as r2 of x. And I'm just going to give you the final answer here. We find that yp2 is equal to minus 2 over 29 sine of x minus 24 over 29 cosine of x. Finally, we're going to look at yp3. yp3, we've proposed, is of the form c e to the 2x. So again, we need its derivatives. So yp3 prime is equal to 2c e to the 2x, and yp3 double prime is 4c e to the 2x. So we substitute this into our ODE. So we have the second derivative, 4c e to the 2x, plus twice the first derivative, so that's plus 4c e to the 2x, minus 4 times the function itself, minus 4c e to the 2x, and that's going to be equal to the right-hand side, which is negative 6 e to the 2x. So we see that the first, these terms here cancel each other out. So we are left with 4c e to the 2x is equal to negative 6 e to the 2x. We can solve for c and find that it is equal to negative 6 over 4, or that is negative 3 over 2. So yp3 is equal to negative 3 over 2 e to the 2x. And so our particular solution for the entire ODE, yp, is just equal to yp1 plus yp2 plus yp3, where yp1, yp2, and yp3 have been solved over here. Okay, the next example I want to solve is this one here. So we want to find yp, so a particular solution for y double prime minus 4y is equal to e to the 2x. Seems fairly straightforward. So it makes sense for us to propose that yp is equal to some constant a multiplied by e to the 2x. After all, that's what the table from the previous video suggests that we do. So let's go ahead and use this. So we have yp prime, and that is equal to 2a e to the 2x. And the second derivative, yp double prime, is equal to 4a e to the 2x. So we substitute this into the ODE. So we have the second derivative, 4a e to the 2x, minus 4 times the function itself, which is the proposed particular solution, and that is 4a e to the 2x. And that's equal to e to the 2x. And we see that the first and second term cancel out. So what this gives us is 0 is equal to e to the 2x. So why did we obtain this result? So it turns out that the proposed form for yp, which is a e to the 2x, turns out to be one of the fundamental solutions to the associated homogeneous equation. So we can check this very quickly. So our associated homogeneous equation is this right here. We have a characteristic equation of the form r squared minus 4 is equal to 0, or r is equal to plus minus 2. So we know that for two real and distinct roots, we're going to have y1 is equal to e to the 2x, and y2 being equal to e to the negative 2x. So what we see here is that whenever we substitute e to the 2x into the left-hand side over here and take its derivative, the result is going to be 0. So we can never use e to the 2x and obtain a non-homogeneous term on the right-hand side. Okay? So recall from the previous video that if the proposed solution, or rather, if part of the non-homogeneous term r of x is one of the associated fundamental solutions to the homogeneous equation, what we should do is multiply the proposed form of the particular solution by the independent variable. That is, what we should do is propose that yp is equal to ax e to the 2x. And this, in principle, should take care of the problem that we just encountered. So let's have a look at that. So again, we will need to take some derivatives. So we have yp prime. And so we'll have to use the product rule here, because we have two functions, x and e to the 2x, that are being multiplied by each other. So what we find is that we have a multiplied by e to the 2x plus 2x e to the 2x. And it'd be good practice for you to pause the video and try to get these on your own. Just make sure that you're on top of taking derivatives. Okay, and the second derivative, once again, we take the subsequent derivative. And that gives us 4e to the 2x plus 4x e to the 2x. Okay. So we're going to substitute yp double prime and yp into our ODE over here. So we have 4a e to the 2x plus 4a x e to the 2x minus 4 times the proposed form of the particular solution. So minus 4ax e to the 2x, and that will be equal to the right-hand side, e to the 2x. So we see that terms 2 and 3 cancel each other out. So we are left with 4a e to the 2x is equal to e to the 2x. Can further cancel these, giving us a is equal to 1 over 4. So the appropriate particular solution, yp, is equal to 1 over 4 x e to the 2x. Now remember that this is just part of the overall solution. Okay, remember that for a non-homogeneous ODE, you superimpose the homogeneous solution with the particular solution. So we found our fundamental solutions, which are e to the 2x and e to the negative 2x. So we can just say that y of x is equal to c1 e to the 2x plus c2 e to the negative 2x plus the particular solution 1/4 x e to the 2x. And this is the general solution for our second order linear non-homogeneous ODE, which we found using the method of undetermined coefficients.